Hello and top of the morning to you. I'm Sir Reagan Parrington of Arlington, Texas, and today I'd like to present a short clip from Sir David King at Cambridge. Sir David King will illustrate a brief history of our climate emergency and underline two very important points. One being that we are now way past the threshold for safe conditions for humans and virtually all other life on Earth. When you add methane into the mix of greenhouse gases, we are easily over 500 parts per million in our atmosphere, which means it's already baked in, just like the title says. And the second underscored fact is that we have to develop, implement, and build upscale carbon sequestering technologies within the next few years. Because as we can see from the graph here, and considering exponential growth, it goes directly up. And I'm going to follow this trend onto 2030, where it will be pure hell. So, without further ado, I'm going to let Sir David King do the rest of the talking. And, of course, please like and subscribe and share for all the normies to understand that we don't have much time left. And so, once again, thank you and enjoy.
Good morning, good afternoon, good evening, everybody. Delighted to be addressing you today on this critically important subject. What I'm going to do is just very quickly run through a bit of the science of climate change, where the current big challenges are, and then what we're doing to try to deal with this enormous challenge to our civilization. So first of all, let me start with just telling you a little bit about the science. By the time we reached the end of the 20th century, 19th century really, but 20th century, we had really a full understanding of the nature of climate change. By 1820, we had the great French mathematician Fourier showing that he could calculate the temperature of the Earth, knowing the amount of energy arriving from the sun and the amount that was absorbed by the Earth. And he found he had to use a parameter to describe how much of the energy absorbed from the sun was captured by the atmosphere. 1860, the Irish scientist Tyndall discovers it's not the whole atmosphere that captures that energy, because oxygen and nitrogen cannot absorb any heat energy, any infrared radiation. And so what he discovers is that it's these minority gases, the so-called greenhouse gases, that capture the energy and keep the Earth about 30 degrees centigrade warmer than it would otherwise be, about 30 degrees centigrade warmer than the surface of the moon. And so as we move forward, we go to 1898, when the first calculation is done by the Swedish scientist Svante Arrhenius. What Arrhenius does is to simply sit down and say, what if the greenhouse gases in the atmosphere were increased by humans using fossil fuels, which is a process that had obviously begun well before then. And he concluded that if we were to double the amount of greenhouse gases in the atmosphere, the temperature rise would be of the order of 4 to 5 degrees centigrade. And today, with all of the massive computers that are available and the much more detailed understanding of climate science, we know that the figure is more like 3 to 4 degrees centigrade if we were to double the amount of greenhouse gases in the atmosphere. So now I have to switch over and say, where are we with greenhouse gases today? Back in the pre-industrial level, I'm just going to give a few numbers now. Greenhouse gases in the atmosphere were at about 265 parts per million. Mostly, the vast majority of it was straightforward carbon dioxide. And as we arrive at today, the number is actually just over 500 parts per million, about 508 parts per million, if we add in, as we have to do, the other greenhouse gases that have been emitted as a result of human activity, and in particular methane. Methane levels are now at quite a high point. Without methane, we're at 415 parts per million. Include methane, we're over 500. And so where we are today is already at a point where we understand the temperature rise could well be 3 to 4 degrees centigrade, even if we were to emit no more greenhouse gases into the atmosphere. A little point in paleoclimatology, if we go back 4 to 7 million years ago, that's the last time we know that the planet was at a greenhouse gas level similar to where we are today. And temperatures then were about 3 to 4 degrees centigrade higher than today. But sea levels, and this is going to be a point I'm coming back to, were about 25 feet higher than they are today, about 7 meters higher. So I now come to discussing the real challenge that was not understood properly 10 years ago. There were some voices that were saying we've got to expect this. What is happening in the Arctic Circle region in particular? Let me dwell on this one topic, and then I can get through in a brief period of time. So in the Arctic Circle region, we now know that the loss of the ice that was covering the Arctic Sea around the North Pole has now proceeded far more rapidly than any of the climate scientists predicted back 10 to 15 years ago. There's a big positive feedback in that melting. And so today, during the Arctic summer, roughly 50% of the Arctic Sea is exposed to sunlight. Now, what does that mean? It quite simply means that the Arctic Circle region as a whole, that whole region of the planet, is now about 3.5 degrees centigrade above the pre-industrial level. We're already at that point that we all said many years ago we should never reach, a region of the planet having reached 3.5 degrees centigrade above the pre-industrial level. The overall average for the whole planet is now 1.1 degrees centigrade above the pre-industrial level. So this region of the planet, much warmer than the rest, and the reason is very simple. That blue sea, the deep blue sea of the Arctic, is now absorbing sunlight very, very efficiently, 80 to 90%, whereas the ice covering it, of course, was reflecting the sunlight back into space. So the North Pole region is now a warm region in the Arctic Circle. And in fact, the Arctic Circle region, which normally has a rather circular vortex around it, keeping the cold air in that region, has now become quite seriously distorted, and it's meandering. So what I show you there is a picture got from our Met Office, just demonstrating that because the North Pole itself is now warmer than the surrounding region because of that Arctic Sea, what you see is that at this point in time, the coldest region of the planet was between Canada and the United States, and certainly not the North Pole. So we've got a dramatic change in the weather systems of the Northern Hemisphere. This polar vortex is meandering. It's not stationary in that position, it's rotating around. And so we're seeing some very strange weather in the Northern Hemisphere. I'm sure you're aware more than we are of the very low temperatures experienced in Texas, -16, -12 in two periods about 4 years apart, 3 or 4 years apart. And that has never been experienced by human beings in Texas before. On the right-hand side is a problem that I will come back to, which is the possibility of methane emitted from the Arctic Circle region. The permafrost, which is the state of the Earth in the northern regions of Russia and Canada, the permafrost contains methane in the form of a molecule, methane hydrate, which decomposes. It loses the water that it's attached to, decomposes at a temperature below the melting point of ice. And so if you walk on the permafrost now and throw a match onto it, you can see a lovely blue flame spreading over the permafrost region. That's methane escaping from the region. Very low density, doesn't stay lit for long. And on the left-hand side, here's the biggest risk of all at the moment, which is that sitting there in the Arctic Sea, now during the polar summer, exposed to that blue sea, is Greenland. And Greenland has enough ice that if all of it melts, global sea levels will rise by about 7.5 meters, by about 25 feet, 23 to 25 feet. So what we see is already happening in Greenland is the loss of that ice faster than was originally predicted. So there's a positive feedback. Let me just very quickly say, when the ice melts in Greenland, that's such a big ice sheet that it starts forming lakes. And as the lakes get deeper, the color gets bluer, reflecting the sky. And so it absorbs more and more sunlight as it melts. So there's the big risk that sea levels globally will now rise far more rapidly than we'd previously anticipated. If I could take the next slide, I'll just say something about methane emissions in the permafrost region. I was at the Arctic Circle meeting in 2019 when the Russian Academy had sent a group of scientists to the meeting to report on explosions taking place in the Yamal region of northern Russia. And these are pictures of the craters left after the explosion. You'll see on the left-hand side, there's basically a crater with not much material around it, because most of that, it looks like there's a lot of earth. It's not earth, it's basically ice and methane. And what is happening is a methane bubble is forming below the ice. And when the pressure on the bubble created by the gravitational force above it exceeds the mass and gravitational force, it blows all the remaining ice out, and all of it enters the atmosphere as water vapor and methane. Now, of course, and the right-hand side actually shows the academicians who were sent to investigate the first release in this way. You see a team of them standing on the other side of the crater, and on this side you see the shadow of the photographer on the other side of the crater. How many of these are formed so far? About 1,000. And that is rising. It was 1,000 by 2018. It certainly has risen since then. Is there enough methane being emitted to actually distort the greenhouse gas level in the atmosphere? Not yet. The danger is that these explosive releases of methane will increase, and then there is enough methane in the Arctic Circle region to raise temperatures by 25 degrees centigrade. I mean, this would be end game, but let's not worry too much about that, because frankly, I don't think that's our biggest worry at the moment. The biggest worry is the melting of ice on Greenland. If I could have the next slide. Here's an example of this. If we look at the impact of rising sea levels and the warming of the ocean surface, we see that the region of the world that is going to be most impacted by rising sea levels is in Southeast Asia. All of the countries in the Southeast Asia region will be impacted. I'm just showing you here Vietnam. And on the left-hand side is the prediction for the annual flooding of Vietnam by 2050, just 30 years from now. The left-hand side is the prediction made 10 years ago. The right-hand side is a much more recent prediction by the same group. And what you'll see is that Vietnam, which is very close to sea level, essentially it's that Mekong Delta pushing that land out, so it's all very close to sea level. The vast majority of the landmass of Vietnam underwater at least once a year. The reason is not only because they have rising sea levels, but of course storms at sea, and in particular the hurricanes that happen in this region frequently cause the sea to be roughened, and therefore incursion takes place further. But worse than that, The hurricanes are picking up energy from the thermal energy of the sea. After a hurricane has passed over the ocean is far cooler in that region. It's picking up the thermal energy into the vortex of the hurricane. And essentially, we therefore see that warming seas due to climate change makes this impact worse in this region. And they have now experienced the worst hurricanes ever recorded by human beings over the last few years, particularly in the countries like Indonesia, Vietnam, etc. And so what we see is that a vast landmass, and this landmass here, Mekong Delta, the biggest rice paddy fields in the world, is a big rice producer for the region. But together, couple that with Indonesia lying very close to sea level, archipelago, we know that Jakarta, for example, will be underwater to such an extent within a fairly short period of time from now that it won't be livable. That's a city with 30 million people. You might have seen the pictures of Jakarta flooded in January and February this year, literally underwater. What we see is that this bustling modern city built out of the rising GDP of that country over the last 20, 25 years will not be livable by mid-century because of frequent flooding. If I look around the major areas, Vietnam, the whole country unlivable. If we look at Calcutta, the first major city that will be unlivable due to frequent flooding. And on the other side of India, Mumbai as well, very close to sea level and very much subject to flooding as sea levels rise. So there's the nature of the big challenge ahead. 200 to 300 million is the estimated number of people in this part of the world, and I'm including Bangladesh, 2/3 of which will probably be unlivable by mid-century. 200 to 300 million people in this part of the world will not be able to live where they are currently living. So we're looking at a major issue of climate refugees. But in addition to that, the loss of rice in the region is going to be enormous. If we look at Southeast China, that is also a region at risk from frequent flooding, and rice paddy fields again at risk in that region. So what we see is the nature of the challenge going forward in time. And what we're doing in setting up the Centre for Climate Repair at Cambridge is setting up a centre which will act as a research centre. We will also do development of new technologies, new projects, but we are also acting as a global hub for actions around the world, working with major universities where we can work on particular projects such as the University of Hawaii, the University of Incheon, the Marine Institute in Goa, but also working with Stanford University in the United States, working with Tsinghua in China, and so on. We are working as a hub on climate repair to see that we can extend these activities around the world. Let me take the next slide, which sets out the objectives of the Centre for Climate Repair at Cambridge. These, I know, sound very grand and very ambitious. I'm going to say they're neither grand nor ambitious, they're simply necessary. Deep and rapid emissions reduction, we're cooked without that. Create new greenhouse gas sinks, and our objective is to restore the atmosphere from 500 parts per million to about 350 or less. That will take us, even if we roll out our technologies very quickly, even if we do that, it'll take us to the end of the century to reach it if we get item number 1 delivered. Item number 3, in the meantime, the poles are unfreezing and we need to deal with that. So we are looking at refreezing the poles. And I know that attracts a lot of wry smiles from people. I can explain how we're beginning to approach that problem. Then, of course, we need to promote agile political investment responses, and we are working on both the political and the financial sectors around the world as we move forward in time. If I could have the next slide just to go through very quickly. The focus of feasibility for our projects is, first of all, technological feasibility. That's research lab work. Secondly, scalability. We're only looking at CO2 removal from the atmosphere if it's possible with that technique to see that we could remove at least 1 billion tons of greenhouse gases a year. And we obviously need to factor into this the cost of doing this. And then thirdly, we're looking at potential adverse impacts. We don't want to be clobbering the earth in some other way, but through these adverse impacts that might occur. And then on the next slide, I'm just picking my favorite for greenhouse gas removal. Everyone has a favorite. And this is ocean surface ion fertilization. We like to imitate natural processes, and this is doing exactly that. When the wind blows over the Sahara Desert and picks up a dust storm from the small dust particles in the sand, and then, for example, over the Sahara, blows over the Atlantic and the wind stops blowing and drops the dust onto the surface of the ocean, held there by the surface tension of the ocean. Within a month, that area is green. Typically, the area would be 50,000 square kilometers in extent. And that green area contains a vast amount of phytoplankton. And before you know what, you've got a massive fish stock. I mean, billions of fish in one of these areas. The reason is the ocean is teeming with fish eggs. Each female fish on average lays 100,000 eggs. And so what you have happening is larvae hatch, most of them die, but in these green areas, they all survive. And so you get billions of fish, they attract the bigger fish from elsewhere. And so you have a massive harvest of fish there. The deposition takes place as calcium carbonate, and we are still to do the experiments to see how much of it does this. And that in that way, carbon dioxide captured by the green material is firmly sequestered. Next slide is showing you an intervention with cloud brightening. And this is simply saying that as we move forward in time, we will need to create white cloud, bright clouds over the North Pole during the polar summer to reflect the sunlight away from the sheet of ice that is formed over the ice during the previous winter. And if we do that year on year, we'd probably have to do it for 40 years. The idea is that we create layer upon layer of ice, and that gives us some comfort going forward in time as we bring greenhouse gas levels down to a decent level. So there you are. I've run through the nature of the challenge, the strategy that we're developing, and we are working on these projects right now. If I could take you to the end of my talk and just say thank you for listening. I look forward to the questions.
So Dave, thank you so much indeed.